Yeah, welcome everybody to the webinar with Maarten Stol from Grain Creators and the ASQF. Thank you for joining us today. The topic Maarten will present to us will be AI Essentials from Technology to Use Cases. Maarten Stol and Marcel Schwarzmeier, that's me from ASQF, will guide you through this presentation. Please feel free to ask questions by using the chat or question function, and we will be happy to answer your questions after the webinar. Now I'd like to hand over to Maarten and enjoy the presentation.
Thank you, and thanks for giving me this opportunity to present. So I understand we have about 30 minutes. I made a selection from some use cases that we did in the field of AI at Brain Creators. I'll cover about maybe 10, maximum 15 minutes with use cases. And the reason that I begin with the use cases is that after that, we will move on to some considerations about context. And with context, I mean, what happens if you have a successful AI application and you deploy it in the real world? What now? You're confronted with certain challenges. And I hope by first giving you a presentation of some use cases, you have an idea of the range of different topics and different challenges, and that as we move on to the context, this is better to understand then. So this is my overview. 4 parts. I'm going to do a very, very short introduction on Brain Creators, just so that you know who we are. Like I said, then the bulk of the first half is example use cases. Then we move on to managing AI deployments in their context. And I'll close off with a short epilogue and some closing remarks. All right, we are Brain Creators. We're an Amsterdam-based AI company. We have been existing under this name for maybe 3 or 4 years. This is already our second AI company. We've been working in the field of AI for quite a while. These are my friends and founders of the company, Jasper and Gerbert. I met them at when we all started the AI Master in the late 90s. So we all studied applied AI at the University of Amsterdam. That's how we know each other. Jasper and Gerbert have been successful entrepreneurs. And when they founded Brain Creators, I joined the team as their scientific advisor. So it's my job to make sure that relevant scientific knowledge keeps flowing into the company and reaches our development team and ultimately our customers. What I want to say before I go into the use cases is, right, AI is very experimental in several ways. So it's in a sense quite new, but it's also experimental in the sense that it's not like programming ordinary software where you know what's going to happen to some degree, you know what to expect, you know how much time you need, because AI and especially machine learning, the behavior of a machine learning application is really dependent on the data that you feed it. And that means that it's a statistical affair, and in that sense, sometimes unpredictable. If a customer gives us noisy data, we need to do quite a lot of experiments in order to clean the data and understand what the possibilities are. So that's why we say, you know, turn your experiments into profitable use cases. Okay, moving on to the use cases. For ease of presentation, I identified 3 main fields that I want to focus on. So there are some back office use cases, something that can, if you allow me, be called Industry 4.0 and supply chain. This is not black and white. You'll see a number of examples that maybe fall into 1 or 2 or maybe more or none at all of these categories. Okay, so moving on to the use cases. First use case, I want to talk about steel manufacturing. This is a quality control use case. So in the upper picture, you see these big coils of steel sheet that are produced by a big steel manufacturer here in the Netherlands. And quality control means that cameras are looking at the finished product as it comes from the presses. It's important for the manufacturer to know the quality of their product because then they can do better trading with it. If you know a coil is very high quality, you can ask a higher price. And if you're certain that a coil has certain imperfections in it, it doesn't hurt so much if you, well, let's say, don't make car doors from it, but instead make soda cans from it. So this is really about computer vision, and it's very much dependent on the images that are being labeled by the steel experts. What we contributed was a tool that recognizes these defects and also helps the customer to label the right images in the right way. Okay, so that's a computer vision use case. I'm going to move on to the next one. This is about radar. So this is about ground radar. You see this sort of lawn mowing device on the left. That's a person pushing the radar over the ground. And the purpose of the device is to understand what sort of objects are lying underground. Now, in particular, our customer is looking for gas pipes. And it sounds a bit strange because you might think that, well, there are maps that show where gas pipes are. But these maps in the Netherlands, they're quite old. They're about 50 years old. And the precision back then was not what we want now. And if, let's say, a farm field has some gas pipes in it, and now we want to build houses on it, poles need to go into the ground, and it's quite dangerous because there's 40 bar of pressure on the gas pipes. So together with our customer, we help develop this tool that recreates a sort of 3D representation of what's happening underground. And in the lower picture, you see the blue lines are the route that the person pushes the device. So you sort of zigzag over the field. And the green lines are the pipes, and the red dots are the positions at which we detect the pipe. And our job is to integrate this sort of very long waving pattern of image into a 3D representation. Similar technology is used for this as was used for the steel manufacturing, but this of course has other challenges, say 3D nature of it and the special nature of radar sensor data. Okay, moving on. This is a completely different use case, and now we're talking about anomaly detection. So anomaly detection is basically just a fancy word for detecting something that is not normal. So you have a baseline of normal behavior, in this case of a telecom network, and whenever there's some deviation from the normal behavior, you want to be able to detect it. And in this particular case, our customer has both a fiber network, so glass fiber, but also a coax network. And the coax network has a particular challenge because if somewhere in the middle of the coax network there is a defect, it can be as simple as a faulty coax connector, then a field engineer has to move into the field, step into a van, drive into your neighborhood and find this particular faulty coax connector. But the coax network is set up in such a way that locating the exact position and place where this fault is difficult. So that means in practice, sometimes a field engineer needs to drive around to multiple locations, do tests, etc., in order to find the right position and the root cause of the problem. The question from the customer here was, can we, by analyzing the data, the behavioral data of the network, can we do quicker root cause detection, because then the field engineer can go straight to the place where he's needed. So this is a different use case than the previous one. This is really about understanding the root causes of your problem. Together with our customer, we set up a tool that not only does this anomaly detection, but also manages the interplay between the machine learning and the more classical, let's say, rule-based approaches that classical engineers had made to understand the behaviors of the telecom network. All right, moving on to yet something completely different. I tried to find use cases that are as different as possible so that you could get a good idea of the wide variety of areas in which current day AI can be applied. This is about news radio. So our customer was a Dutch news radio station, and they had a very interesting challenge. They said, look, every day we're creating about 8 to 10 hours of new radio interviews. So this is spoken audio. But once it's broadcasted, it's gone. Live users, live listeners, when they miss the broadcast, yeah, they might be able to find it back in some podcast on a server, but they realized that very few people do this. So they said, wouldn't it be nice if we have a sort of recommender engine that can generate a personalized podcast for you? So you can use their app, indicate your interests and indicate sort of your user profile, what sort of topics you're interested in. And then when you have time, if you have time, and when you have time, you can say, okay, I have about 1 hour, give me segments from last week that are relevant for me. Now, the AI part in this is that our applications does the speech to text together with a partner. And after we transform the audio into text, we now have to segment the audio on topic boundaries. Because if the AI can, on its own, segment the audio, it can then select segments of audio of particular topics. And in that way, it becomes a sort of automated editor that edits your personalized podcast. So yet completely different, now working with audio and mostly spectral data, but also speech to text was a big challenge. Okay, moving on. This is something else entirely again. So this is in logistics. Logistics, things like parcel delivery, package delivery, they typically face what is called this last mile optimization. So they have a huge chain of distribution centers, etc., in which your packages go. But really, the moment the van arrives in your neighborhood, where to park, how many packages to do for one parking event, etc. This is what they call last mile optimization. And in our case, the customer said, we have a lot of trouble with addresses that are unintelligible. So the address is spelled incorrectly. This is not about character recognition, so that's not what it's about. It's really about address names that are, they come from abroad, they come from a faraway country. People didn't realize the difference between your postal code or your zip code and your house number or something like that. And what we developed for this customer is a solution that allows them to very quickly repair broken addresses, and in that sense find your location quicker. And what you see in the lower image is that we also integrated this with their GPS data. So every time there's a successful delivery at your door and you accept your package, the delivery person presses a success button and a GPS location is tagged onto the address event. And this allows us some kind of feedback where we learn how to better correct and repair addresses based also on successful delivery. So that's the learning component in this use case. All right, moving on. This is again about images. So last January at the Oscars, together with our partner in America called Runway Manhattan, we launched this product. It's called Fashion Brain. Our partner, Runway Manhattan, sells photography, sells photos as a stock photography to magazines. So a lot of independent photographers upload their images, and for the customer, it's important that their clients can search the database in a quick and intuitive way. So it's very important that images are labeled and that you can search by keywords and descriptions, etc. Our computer vision tools, our machine learning tools, like you see an example here, can analyze an image and understand what's in it. So here, for instance, we see there's a man wearing a suit, it says blazer, colored shirts, etc. We can detect different persons, we can detect hairstyles, bags, I hear from development that now even our model to detect earrings and different types of sunglasses, etc., is working. So this is again a way to create value from unstructured data, in this case visual data, using mostly neural network based machine learning technology. I'm moving on because I'm also looking at the time and I want to reach my halfway point, so I'm going to go a bit quicker. This was in medical imagery, so diagnosis improvement. Here we work together with a startup at Amsterdam Academic Hospital in order to improve understanding what type of stroke a patient has had. This is important for speeding up the time in which a patient can be treated for this stroke. So this is again a computer vision task, but now it is three-dimensional. The black image on the bottom you see is actually a horizontal slice, but of course there's many of these slices that make up the image of, well, let's say your head. So understanding where the stroke is and what type of stroke it is allows the doctors to intervene faster and better. Finally, I think this is my last one. This is a project we're working on now, yet a completely different field of application. So this is about waste management. And you have to imagine that waste products could be anything from, let's say, toothbrushes or old phones or adapters or pens and pencils, etc. They are being fed to the robot on a conveyor belt. There's a camera system that attempts to recognize in what sort of category a device belongs. Is it recyclable electronics? Is it plastic? Is it organic material, etc.? And once the classification has been done correctly, an object is picked up by a robot. So that's another challenge. There's a control component to it. Object is being picked up by a robot and put into the right bin. So I think, yes, that was my last one. So looking back on the last 15 minutes, we've seen a wide variety of areas in which AI can be applied. But there's certain things that each of these use cases have in common. And that is why I wanted to talk about what I like to call AI essentials. They're essential in two ways, by the way. So they're essential in that it's important for the use case, the deployment to work. But also essential refers to, well, the fact that I have very limited time. I could talk for an hour about context and managing deployment, but I tried to boil it down to just 4 topics in AI deployment. So I want to begin with this image. So this image, I like it very much. It's from a paper on the topic of hidden technical depth. Now, technical depth is a topic in software engineering also, but it's all the more important in machine learning. Technical depth is basically the price you pay for moving fast quickly. So you have some kind of problem, you make a quick fix, the quick fix works today, but actually you created new responsibilities for yourself and the problem will come back next month, next year, sometime. So technical and maybe do cross-validation and things like that. All that lives in the tiny black square in the middle. But we are at Brain Creators, we're doing this on an enterprise level. So once we run our deployment in the wild, we have to think about automatic data collection, automatic feature extraction, the serving infrastructure, etc. There is resource management. There's all these things that need to work in tandem to make the machine learning application work. And From this big context, I've taken 4 topics that I want to talk about in the remaining 10 minutes. So these are my AI essentials for today. One is about the subject of proxy metrics versus the real world. I'll get into that in a minute. Second is about what is called model staleness, or when models get old because the data in the real world changes. Third topic is about reproducibility of your experimentation pipeline. It's very fine if you have a wonderful model on Tuesday, but if you can't reproduce it on Friday, then it becomes very hard to debug, you see. So that's that. And my fourth topic is about monitoring of the infrastructure dynamics, right? So there's all the topics about let's say the performance of your neural network and how well it predicts, etc. But there's also the underlying infrastructure. If there's a continually heavier demand on infrastructure, that is something that you need to be quite aware of, because it can really ruin a use case. So this is my overview. I'm not going to go into them quickly, but before I do that, I have to give credit to where these items come from. So these are the 2 papers that I will use material from. They're quite an interesting read. I have a few other papers sprinkled in between also. I'll share them in the slides. Yes, so do your offline proxy metrics correlate with actual online impact metrics? So what do I mean by this? So imagine maybe a recommender engine or something that works online and interacts with your users. A user-facing production system's impact is judged by metrics of engagement, user happiness, revenue, and so forth. On the other hand, my machine learning system is trained to optimize a loss metric, such as log loss or squared error. And the reason I put this on the screen is that often it's easy to forget that these are 2 totally different things. You're training your neural network to do one thing, but in the real world, it's going to do something that is slightly different, right? Understanding how these 2 metrics correlate is vital to ensure a better scoring model will result in a better production system. If I have engineers here working very hard to get a better performance on my log loss or squared error, and I have no real idea how these metrics correlate with each other, I have no guarantee that my newer model is going to behave better in the real world. So that's an engineering essential, I would say. Now, one way to measure the offline-online metric relationship is in a series of small-scale A/B experiments using an intentionally degraded model. So I degrade my model, thereby I lower my log loss or my squared error. Now I'm doing a small-scale A/B experiment, and I want to see that this change in this degradation is also reflected in the real world. It's important knowledge to have. Follow-up reading on this one. It's a paper that's already a little bit old, 2012, but I think it's really vital. It's a very short paper, it's concise, it's non-technical, I can recommend it, and it's called Machine Learning That Matters. So this paper warns about the dangers of the over-focus on your benchmark data sets and abstract metrics, and really talks about how can you make your machine learning really matter also in the real world. It's a paper, it's aimed at academia, but in industry where we operate, it's even more vital. All right, moving on to my second essential. Is the impact of model staleness known? Now, what do I mean by this? So many production machine learning systems encounter rapidly changing non-stationary data. So you train on data from last month, or maybe on data from last year. You have a rather strong assumption, and that is that last year is representative of the coming year. This assumption holds to some degree. It is also violated to some degree. And you need to be aware of the impact of the strength of this assumption, right? So an example could again be a content recommendation system or financial application, but it could equally well be, the quality control in steel manufacturing. If the ovens that create the steel change their temperature, or maybe the iron ore is changed, that means that the data is no longer fully representative. Right? So for such systems, if the pipeline fails to train and deploy sufficiently up-to-date models, then we say the model is stale. It's basically an old model. And understanding how model staleness affects the quality of predictions is necessary to determine how frequently to update your model and on which data to retrain. Right? Should you retrain on maybe the last month or only the last week? Maybe only on yesterday's data, but then that data is so small that you don't have enough. So there's a trade-off between having data that's up to date and data that's old. You need to understand this about your data, and you also need to understand the impact of deploying a stale model. Right? So one way of testing the impact of staleness is again with a small A/B experiment with older models. Testing a range of ages can provide an age versus quality curve to help understand what amount of staleness is tolerable. Now, there are other methods to analyze more refined types of concept drift. So concept drift is a technical term from statistics. It basically means that your data distributions are changing. The real world is different from your training data. One approach could also, for instance, be to detect significant approaches in the confusion matrix. So a confusion matrix is again, is a concept from machine learning. Basically means that if you are working with a classifier, you can see which classes it is confusing. Now, if you monitor this over time and you see that there's a new pattern in which classes are confused, this could be a trigger indicating there's some type of concept drift going on. Again, here's a follow-up reading. I'm not going to talk about this paper because I'm looking at the clock. My third essential, are training and experimentation reproducible? So ideally, training twice on the same data should produce two identical models. Deterministic training dramatically simplifies reasoning about your system. For example, your feature generation code, if you're optimizing this is a delicate process. If you want to verify that you're doing this in a correct way, it's very good that you can train to an identical model. Yeah, then you can do some type of diff testing. Again, in classical software engineering, this diff testing only relies on code, but now in machine learning, it relies on data. And it's much more difficult to get a grip on the type of behavioral change that your model undergoes when you're relying on data. So unfortunately, model training is often not reproducible in practice, right? You're working with non-convex methods like deep learning, or even more classical methods like random forests. This can manifest as a change in aggregate metrics across an entire data set, or even if the aggregate performances appear the same from run to run, as changes on individual examples. This sort of lack of reproducibility can make debugging and understanding your system quite difficult. Other issues related to this are, for instance, your random number generation, right? You're initializing your models with random numbers. You think that you're keeping your seed, but maybe there's something like underspecified initialization order. You're giving away some tasks to underlying graphical processor units. They optimize things in a way you don't control, and in this way, reproducibility could suffer. Now, it's not black and white. I would advise to have as much reproducibility as possible. It's never going to be 100%, but just keep in mind that this is an important item if you want to understand and debug your systems. All right, here's again a follow-up reading. It's an interesting article on Towards Data Science, worth reading if you want to understand this topic. Moving on to my fourth one, I have a few minutes left, I see. Monitoring training speed, serving latency, and RAM usage. So this is really about understanding the behavior of your infrastructure. Computational performance, as opposed to predictive quality of an ML system, is often a key concern at scale. Think of camera systems and the server hardware that need to process this data. It's quite easy to buy another, let's say, 100 cameras, but if you then also need to have 100 graphical processor units, this is very expensive. So you need to use them the best way that's possible. And if they start lagging, if they start running slower, you need to detect this quickly, right? So I have a few technical points here that I'm going to skip over to. The message overall is there's more to machine learning than just a predictive quality. If you deploy these things in the wild, you need to keep monitoring. If you train every day, does this speed up or get slower? Do your RAM requirements move up, etc.? Okay, so these were my 4 essentials. I am almost at the end. I have a few moments left for my epilogue, but Marcel, you can cut me short whenever the time is done. So one last thing I want to talk about is what I like to call the application gap. So my department, so I'm the scientific advisor of the company. Mainly my work consists of selecting research papers and helping our development team turning them into commercial products. And I'm very much aware of the gap between academic research and the demands of industry. Now, I put this slide in because recently I was in an interview on the radio. I was talking to a professor and he named speech to text as a technology that was basically fundamentally solved. And I was quite surprised by this because I know that we are struggling with keeping speech to text up to date. Every month there is new words in our language, there's new expressions. Speech to text is basically never solved. And I was struck by the difference between our different ways of thinking about it. From academia, it's maybe less and less an interesting topic to publish on, but from an industry point of view, it's not at all solved yet. So there's this gap, and we at Brain Creators, and company like ours, will always be trying to bridge this gap. That's what we do. That's our work. Then I want to finish with this quote by Andrew Ng. So I hope I'm pronouncing his name correctly. Andrew Ng is a famous founding father of deep learning. And this quote struck me very much, right? So one of his important quotes is AI is the new electricity. So that needs no explanation. But I was very surprised by his quote, we have enough papers, stop publishing and start transforming people's lives with technology. And this is exactly what we're doing at Brain Creators, where we see that a lot of companies are still at square one with applying machine learning, while the research community and academia are publishing very beautiful papers. Now, I don't want them to stop publishing, but I do think that there is enough papers published now that we can really start making a difference in society. And I want to end with this provocative slide for your audience. It's a bit of a jest. So this is how I experience the competitive landscape in AI today. There are companies that are working very hard on AI, but I just want to bring home the point that there's so much opportunity. If you are working in AI, or if you're considering working in AI, I want you to understand that there's a vast field that we can expand into, make interesting new things, learn how to make money in new ways by getting knowledge from data. And the landscape is basically very big, and there's a lot of opportunity for all of us. And that ends my presentation. So I thank you very much for your attention. And if I'm looking at the clock, I'm not too much over time. Thank you very much.
Thank you very much, Maarten, for this nice presentation and the use cases. I think it was, for me, it was very interesting to see what AI is already in. And yeah, we are open for questions now. So if you have any questions, don't hesitate to ask. Put it in the question field, and Maarten, be sure that he can answer the question if you have some.
Yes, so let me see if I can, do I hear or do I see the questions?
I can read them for you when they're popping in. You have like a small window with question. What says question?
Oh yeah, I see. See if I can open that.
The first one, we had a bit trouble in the middle. There was your voice was gone for some seconds, but this was connecting was coming back. So
Very good. Yeah, and if you can help me translate the questions from German, that would be really nice.
Okay, No problem. But so far, this discussion you see there was about the quality because we was not hearing you for some seconds.
Yeah, yeah.
Good.
All right. Well, also you can see my email here at on the slide. So if the audience doesn't have their questions right away, feel free to send me an email later on. Sometime in the next week, I can still get back to you.
Okay. But we have some questions. So the first one is, have you ever deployed an unsupervised learning, self-learning system to a customer?
Yes, so we have. So very good question. So maybe for the rest of the audience, typically the image classification task, you know, like the steel manufacturer, that was all supervised because we had the labels of the images and all we needed to do was predict new labels on new data. But I talked to you about the use case for telecom. This was mostly unsupervised. So this was this anomaly detection use case. And there was two reasons we had to go unsupervised. There were almost no labels. Labels were expensive to make. But also, when you're working with these telecom data, all of this is time series data. And that lends itself a little bit easier to an unsupervised approach, because if you have time series data over the last month or over the last 6 months, there are algorithms that can learn a baseline and understand what is normal fluctuations. And in that sense, you don't need a human operator to label these cases for you. Now, what you see in practice is that it's almost always a mixture of unsupervised and supervised. So we do the anomaly detection with standard anomaly detection unsupervised algorithms. But in the meantime, we offer our customers customized software so that they can provide labels if they want to or if they have time. And then the combined system of both supervised recognition and unsupervised anomaly detection provides the final functionality for the end user. So it's often a combination of that. Yes, I hope that answers the question.
Okay. How do you deal with somehow unknown future behavior as such as unsupervised AI?
So I'm not sure I fully understand the question, but yeah, the thing is, of course, you have always have to make certain assumptions, right? So, for instance, coming back to the telecom use case, we are seeing these time series data. So they were basically things like signal to noise ratio and things like that, electrical information on the network. We have to make certain assumptions about that. So unknown future behavior could simply be things that lie outside of your assumptions. Now, whenever we work with a customer, we are fully dependent on the customer for domain-specific knowledge. As you've seen from our use cases, we work in many different industries. We are not experts at all in these industries. We help our customers to adopt this technology, but to make it really work very well, we have to work together with their domain experts, and they provide us with a set of reasonable assumptions. Now, of course, it's still important to have maybe some triggers or some way to detect really funny behavior in the data or stuff that you never did. And typically what we're doing now is we're now engineer a completely new solution. And this in a sense is a nice illustration of how AI has come a long way in the last, let's say 10 years, but it's not fully matured yet in this sense that these things are not automated yet. There's still quite a lot of work to be done for data engineer, data cleaning, etc. And especially if models are deployed in the real world, they still need some degree of attention. I hope that answers the question.
I hope so too. One question is, what is your strategy to validate your trained AI?
Okay. Yeah, so again, this is maybe points back to this topic I had about the correlation between the real world metrics and the metrics you use on your data. So I think it's really, this is at the heart of it. So the first thing we do is we make an assumption, right? And we assume that performing correctly on the test data that we have will to some degree reflect into the performance in the real world, right? But real validation of a deployed model is something you have to do live. And this also, I think, it comes back to a really fundamental point, and that is that it's very difficult beforehand to know the behavior and the performance of your machine learning model. And in this sense, it is really very different from classical software engineering, where you can make a design and reason from the code and reason from the design and understand its behavior. And this also points to a fact that, you know, our sales team sometimes has difficulty in bringing this point across, because yeah, you have to imagine what happens if we sit at the table in a let's say pre-sales meeting, and the potential customer says, yeah, we want certainties of the performance, we want promises and deliverables, and we want to have guarantees in life. So that is difficult with current day machine learning. On the one hand, it offers a lot of opportunity to discover new patterns, to automate complex tasks, but the price you pay is that you sacrifice a certain amount of guarantees and certainty in life. And the real validation of your machine learning application needs to be done live to some degree. Now that, yeah, if it's a critical application, a really critical application, then there is a risk involved. And together with the customer, we need to sit down and understand these risks and prepare for them as best we can.
Okay.
I hope that answers the question.
I think so. Good. I think that was the last question. Maarten, thank you very much again for the presentation. And yeah.
Yes, and thank you very much for the opportunity. I enjoyed making this deck. Again, for the audience that's listening live now, or maybe later in the recording, if you have any questions about what we do or the rest of our team, feel free to visit our website or send me an email. I'm happy to answer your questions. Thank you.
Thank you. Okay, then this was the last webinar session we had for the ASQF NetWeek. Please give us feedback if you enjoyed it, if we can do better, or if you like something very specific. Yeah, thank you very much for this nice week, and thank you, Maarten, again for this presentation, and have a nice weekend. Thank you, everybody.
Bye-bye.
Bye.